Hey guys, today we are starting chapter 5, which is all about something called systems of linear equations. Specifically today for 5.1 we are looking at what is a solution, and kind of simultaneously we'll look at how we solve by graphing for a system of equations. So first things first, what is a solution? So we've been asked to identify solutions before, and if we were trying to solve or find a solution or check if something was a solution, we've got a couple of different options. We could plug it in to see if it works in the equation, or we know if we're looking at it graphically, we know that a point is a solution when it's on my line. So here they want us to identify which line contains the point 4, 2. So I'm going to kind of kill two birds with one stone. I'm going to graph each of these. I'm going to go ahead and use a different color, blue for the left, red for the right, and just graph each of those lines and then see if 4, 2 is on either of those. So here I've already got my red set up here. So negative 3 over 2x plus 8. If you remember back from last semester, 8 would be my y-intercept. So up 1, 2, 3, 4, 5, 6, 7, 8. That's my y-intercept right there. And then negative 3 over 2 is my slope. So down 1, 2, 3, right 1, 2, 3. Oops, sorry. Right 2. Rise over my run. So then I can go ahead and grab my, don't know why it's not doing that, grab my ruler, line it up as best as I can, draw my line, connecting those 2 points all the way across, and go ahead and put my ruler away. So I've got my blue line drawn there, my red line drawn there. I'll repeat the process again with my blue, negative 3x minus 10. So negative 10 is my y-intercept, so down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is right there. And then 3 is my slope, which we know is really 3 over 1. So I can go up 1, 2, 3, and over 1. I'll grab my ruler again. Oops, page keeps moving on me here. I'll go ahead and line that up as best as I can. Yep, I think right about. That looks good. So I've got that drawn, arrow through the ends. So now that I've got both of those sketched, I'm looking to see is 4, 2 a solution in both of those two equations, and really, does the line contain it? So I'm going to go ahead and highlight 4, 2 with my yellow pen here. So right 1, 2, 3, 4, up 1, 2, and hey look, that's actually the point where they intersect. So in this case, which point contains it? Both. Both y equals 3x minus 10 and y equals negative 3 over 2x plus 8 contain the point 4, 2. Now we're going to look and see, okay, that's nice graphically, and some of us are fine with that. Others of us want to avoid having to graph again like the plague. So we want to see another option on how we could figure this out. So if we're trying to figure out which line contains the point 4, 2, like I had said earlier, we could just check to see is 4, 2 a solution in that equation. So when I plug in my point, which again we know x, oopsie, my coordinates are always x, y. If 4, 2 is on the line, y equals 3x minus 10, then when I plug in 2 for my y value and 4 for my x value, it should work in that equation. So I'm just going to divide my space up here so I can keep it separate, but I'll still use blue for the left one here. So if I plug in 2 for my y, 4 for my x, I should get an equation that is true, which I do end up with here, 2 equals 2. So yes, that is a solution to that first one. Sorry, I didn't really talk my way through that first one. I'll go ahead and do that with my second one. So same thing over here. If I plug in my 2 for my y value, my 4 for my x value, I'm just going to go through now and simplify each side. So negative 3 over 2 times 4, well, that 4 and that 2 are reduced to just a 2 in here. So 2 equals negative 3 times 2, which is negative 6, plus 8, which gives me 2 equals 2. Again on the right side. Now, it's just a coincidence here that they both are 2 equals 2. It could be totally different numbers. What we want to make sure of here, if it's a solution to that equation, it works in either of them. So this could have been -4 equals -4 on one side, 17 equals 17 on the other. It doesn't matter what the numbers are relative to each other. It just matters that on that equation, both sides of your equation are exactly the same. So in this case, again, we could say both. Oh, good Lord, that's thick. Let's try and skinny you back up a little bit. There we go. All right, so getting into some vocab stuff. So kind of what we did was already previewing a system of equations. So a system of linear equations is a set of equations, a set of two or more linear equations in the same variables. So we're going through and you're having two different equations. So we saw that again up in this previous problem. Y equals 3x minus 10 and y equals -3 over 2x plus 8. Those are two different linear equations, right? They're both lines. And they use the same variables, x and y. Now, we'll use some problems, we'll use just x and y, most of them actually. Others will use different variables. But the important thing here is that they are both the same. So I have these two different situations, but the x and y values mean the same thing, which means if it's a solution to one, it needs to be a solution to the other. And we'll get to that in a little bit. But just know that if it's a system of linear equations, it's got two or more equations that are linear, and they have to have the same variables. A solution of the system, not just of one of the particular equations, a solution of the system means it's an ordered pair. Again, if we're dealing with two equations, we have two solutions, x and y. That's a solution to everything in the system. So it is an ordered pair that is a solution to all equations in the system. So it has to work for every equation in my system. If it works for one of them, but it doesn't work for the other one, then it's not a solution to the system. The solution to a system has to work for everything in that equation. So if we go back to the example we were working on here, y equals 3x minus 10, and y equals -3 over 2x plus 8. The point 4, 2 is a solution to the system because it is a solution to both equations. Right, that's one explanation to it. Another thing that we are going to look at in just a little bit, if you noticed on that very first one, we'd also say that this is option 1. We'll say ... It is where the lines intersect. So in order to graphically, on the graph, in order for it to be a solution of the system, it has to be the point where those two lines intersect. So if you look back at that first one, again, our lines intersected here at 4, 2, which means it's a point on both of the two lines. Right? It's an x and y value that work in both of them. So that's why it's a solution. So those are the two explanations, the two rationales that you could do. So again, just doing some practice here. We're asked to identify if -3, 2 is a solution to the system. So our equations here are y equals 2x plus 8 and y equals -x. So you've got these two options. I'm not going to make you do both of them. You've got kind of two different options. You can either solve by graphing, so you can answer it by graphing. So graph both lines, see where they intersect. If they intersect at that point, yes, it is the solution. Or you can do it algebraically. I'll show you examples for both, just so we get some more practice in there. And really kind of which one you're doing is kind of determining which one they're really asking you to do. So for this first one, I'm going to do it algebraically. So this is really asking, does negative 3 comma 2 work in both, oops, there's no e in both equations. So I'm going to, again, divide up my space here. On the left side, we're going to plug it into one of them. On the right side, we're going to plug it into the other one. So if I plug it into y equals 2x plus 8, y equals 2x plus 8 is my equation. 2 for my y value, negative 3 for my x. 2 equals negative 6 plus 8. So 2 equals 2. Yes, so far so good. It's a solution to the first one. On the right side over here, my equation is y equals negative x. So my y is, my y is 2. My x was negative 3. So 2 equals negative 3, which is 2 equals 3. That does not work there. So unfortunately, we have to say this is not a solution. Because it doesn't work in both of them, it is not a solution. It has to work in both of them in order to be a solution. Okay? So let's take a look at number 2. Another example here. So now our equations are y equals negative 1/2 x minus 2 and y equals x plus 4. So if I wanted to do this the other way, if I want to solve by graphing, this is really asking, do the lines intersect at negative 4 comma 0? So you're going to go ahead and graph negative 4 comma 0. Sorry, you're not going to graph negative 4 comma 0. You're going to graph both of the two lines and see where they intersect. So I'm going to do top in blue, my bottom one in red. So my blue graph, negative 2 is my y-intercept. Negative 1/2 is the slope, so down 1, right 2. Or, up 1, left 2, up 1, left 2. You want to keep going with that pattern. I'm going to grab my ruler and just do both of the ruler, like drawing my lines both at the same time. I'm going to go ahead and just plot the other points. For my red graph, y equals x plus 4. So 1, 2, 3, 4 is my y-intercept. Down 1, over 1, or up 1, right 1. You can see here again, I'm kind of doing it just to preview it, but I can see they are going to intersect there at 4 comma 0. So I've got 45 degrees. I got lined up nicely. Draw my first line. Turn it up over here. There we go. We got it nicely there. So I can see here they do in fact intersect right here, and this point is negative 4 comma 0. So yes, or solution, depending on how they phrase it. Make sure you guys are just being careful. If it's phrased as a, is this a solution, like it is here, you could answer with just a yes or a no. You could, if it's phrased, like I think the textbook usually likes to phrase it more so as identify if this is a solution, then you'd have to say solution or not a solution, not necessarily a yes or no. So yeah, that would be what it looks like. That's everything kind of without a context. And on your homework, which is the worksheet that's attached, I'll be posting it here on Classroom, but you also have a hard copy of it you should have received last week on Thursday. It is just a worksheet. The front side, I think, are 3 or 4 problems similar to these two. Here's this point, here's your equations, is this a solution? The second half is going into some problems with a context. So these are going to be more so like word problems. And with these, the more important thing right now are going to be being able to extract that information and write an equation for it. So we're going to just jump into some examples. We've got Fiona that bought 2 different sunflower plants. Their height and growth rates are shown below. So we've got sunflower A that starts off 8 inches tall and grows 3 inches per week. Sunflower B is 14 inches tall, but only grows 2 inches per week. So if we're trying to set up kind of what the variables mean and then be able to write our equation, we want to make sure, especially with a system, that we're dealing with the same variables. So our x, y, m, and b, unfortunately, is cut off here on my page, maybe yours too. They have to mean the same things. So in this situation, I know that my starting value is my growth rate, my starting value is that starting height. And we talked about last semester how when we're setting up these equations, if we have a rate, that's going to be our slope. If we have a starting value, that's going to be my y-intercept. So my b value here is going to be my starting height. It's H-E-I-G-H-T. H-E-I-G-H-T. Starting... Oh, let's work smarter, not harder, right? Starting height is given in inches. So my growth rate is a rate, right? So that's going to be my slope. Growth rate, that's going to be in inches per week. I'm just writing in parentheses there. I'm just indicating what my units are, just to keep it consistent. So then my x and y values, I need to figure out what those things represent, because that's going to be important when we're answering questions later on. So we know our two things that are changing. We're going to be measuring how tall the flower is, and then in this case, if it's talking about how much is growing over time, time would be that x value. Because we always know if we're dealing with time, it's always going to be the x value. So in this case, time is going to be our x value in weeks, which means the height of the sunflower in inches is going to be that y value, which makes sense. If our input is time, our output would be our growth height, because as time goes on, that determines the height of the flower, not necessarily the other way around. We couldn't put in a height, and then that determines how long, like how many weeks have gone by. So you can just, rewrite them or just like put little quotation marks. I'm going to kind of cheat since I'm on my computer here, and I can, let's go ahead and copy. Come on. Can I not do this here? Why aren't you working for me? Maybe I can't work smarter. Well, I guess I'll just do it the old-fashioned way like you guys do. Quotation marks. Yeah, exact same things here. Because copying and pasting doesn't seem to want to work on my note-taking ability right now. All right, so if we now know that information, writing our equation becomes really easy, because if our growth rate is 3 inches per week and our starting height is 8 inches, our equation for sunflower age becomes y equals 3x plus 8. Our equation over here is just y equals 2x plus 14, because that's our growth rate and our starting height. All right, so I'm going to go ahead and rewrite those. Y equals 3x plus 8. Y equals 2x plus 14. So you guys probably don't want to jump back and forth. If we're now looking to try and identify, we've got to answer these three questions. What is the solution? What does the solution mean? And then can we prove it algebraically? So we can do this a couple of different ways. We know from the previous problems we were looking at, identifying if it's a solution, we know two different ways. It either could be plug in an x and a y value to be able to identify that it works in both of my two equations, which is, I think, the easier way of doing it, but that's only if we have numbers to check. Right now, just looking at these two equations, you've got no idea what x and y values you could plug in to make it work in both of the two solutions. So what we have to do then, if we're trying to figure it out the first time around, is that other option. We could check our solution by graphing. So in this case, that actually does work for us, because we saw that if it was a solution to the system, it's where my two lines intersect on the graph. So what I can do now, I'm going to go ahead and graph each of these on this graph and figure out where they intersect, because that gives me an x and y value to go off of, and then I can check my answer with algebra. So before I do this, I'm just going to label some stuff in here. I prefer that you do it this way, especially when you've got a context to it, labeling your axes. So here my x-axis is going to be, time in weeks. My y value, this is going to be height of the flower in inches. I'm going to go ahead and actually change one of these color-wise. So I'm going to say sunflower B is in red, just so it's easier to distinguish the two of them. All right, so if I go ahead and now I'm just going to graph each of these. So for my y-intercept for the blue graph, which is sunflower A, it started off at 8 inches tall, and it grew 3 inches per week. So here I have to be careful because 3 inches would be up 1.5 blocks. Right, this would be the next week right here, and then over a week. But I don't want to use that point to draw my line just because it could be off a little bit. I like using those nice grid marker points. So I'm going to go up another 3 inches and over another week. Okay, just to make it easier. So here I can see that I went up 6 inches over the course of 2 weeks, just to, again, pick out some nicer points. And if you want to, on these, just because graphing is not as precise if you don't line it up quite nicely, I like to just continue with that pattern. So I went up 6 inches over 2 inches, or over 2 weeks. So up, really, it's kind of up 1, 2, 3 over 2. Up 1, 2, 3 over 2. And then that's going to be off my graph. Now, I know that's a little bit confusing because my slope doesn't look like it matches, but that's because of how my graph is scaled. So if you're scaling your own graph and you make everything just scaled by ones, you can do the same slope pattern, right? Just up 3 over 1 for instance, the slope of 3. In this case, I just have to be careful because it is not scaled equally. So now for my for my red equation for sunflower B, it started off at 14 inches tall, and this one's nice and easy. I'm just growing 2 inches every 1 week. So you can see I'm just going to go up 1 box over 1 box because that's up 2 inches to 16 and over 1 week. And you can kind of continue and I'm just going to keep making some dots. You obviously could stop at any point and just draw instead. But we're going to go ahead and grab the ruler. Since I'm already in red here, I'm going to go ahead and draw that one first. There's you want to lock in here. There we go. That's not perfectly 45, is it? That's all right. There we go. And then we'll switch over here to blue. So you can see those are my 2 graphs, and then right here in yellow, this point right here is where they intersect, which if we look at the coordinates here, this is a y value of 26, and then it's right 1, 2, 3, 4, 5, 6. So 6, 26 seems to be my solution. So at 6 weeks, they're both 26 inches tall. So my solution, I'm going to go down here. Change my color here. Let's do green. So 6, 26 was the solution. And I kind of just said that. What does the solution mean? So here we're talking about going back to what it means in the context of the problem. So 6 being my x value and 26 being my y value. If 6 is my x at 6 weeks, y being 26 means 26 inches. So you can say at 6 weeks, or maybe after 6 weeks, they're growing them at the same time. After 6 weeks, both sunflowers are 26 inches tall. So that would be what it means in the context of the problem. After this much time, both of them have a value of this. Proving it algebraically, well, that's pretty straightforward because we just got done doing that. We're just showing that 6, 26 is a solution in both of the two equations. So let's go ahead and divide my space. In my blue equation, which was y equals 3x plus 8, if I plug in 6, 26, well, 26 equals 3 times 6 plus 8. Well, 26 equals 3 times 6 is 18 plus 8. Hey, that's all nice. 26 does equal 26. We're happy with that. Over here, my other equation was y equals 2x plus 14. If I plug in 26 for my y, 6 for my x, oops, that's supposed to be a 14 over here. That gives me 26 equals 12 plus 14. And hey, look at that. We're all happy. 26 does equal 26. That is proving it algebraically. So I know that's a lot of information. It's a really long video, which is why I'm giving you guys the whole class period to be watching this. The homework, again, like I said earlier, it's the worksheet. What is a solution homework? Again, it's half of the problem. The front side are all those problems where you're just showing or determining if it's a solution or not. The back side is similar to this, but really you're just working on taking some contexts and being able to describe what those variables mean in the context of the situation, and then what would the solutions mean. You don't have to necessarily find the solutions, just tell me what they would mean in the context of the problem. So that is all I have for you. As always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, making sure you guys are reaching out and letting me know. And have a fantastic day. We'll see you soon.